So this you have already seen that when you apply a boundary operator on a triangle, its boundaries are edges, right? More specifically, the linear combination of its edges are the boundary of triangle, right? And since it's a two-dimensional, so we have written a subscript 2 here. One thing you notice that when I applied boundary operator on these two simplex, the whatever we got in result is a linear combination, and this linear combination of is made up of v1 v2 v0 v2 v0 v1, which are nothing but basis of our c2, right? So uh, the c2 basis of our c1, in c1 our base were v0 v1 v0 v2 v1 v2. If we do any if we take any linear combination of it, we have given uh, coefficient of v1 plus 2 plus 1, coefficient of v0 v2 to minus 1, and coefficient of v0 v1 to plus 1. So it is one possible combination, one possible linear combination, and we got this uh, one dimensional uh, algebraic group, right? So we can say that on applying boundary operator from dimension 2, we have reached till to dimension 1. So in general we can say that on applying binary operator on a k dimensional uh, k dimensional vector, we get k minus 1 dimension, right? So uh, we can say that this boundary operator is taking vectors from ck vector space and mapping them to vectors of ck minus 1 vector space. So this del or boundary operator, which is applied, which is meant for this uh, vector space of k dimension, when we apply over it, it reduces the dimension by 1, and whenever we reduce the dimension by 1, we get the vectors of this vector space, right? So vector this vector, or I can just chain this k chain belongs to c1, and this was a basis vector of c2, so we went from c2 to c1. So in general we are going from ck to ck minus 1, and for each vector space ck we have a del k. For c2 we have del 2, for c1 we have del 1, for c0 we have del 0, right? So one new term that we will introduce here is chain complex. So basically chain complex, uh, in chain complex we take all the possible uh, vector spaces, vector spaces over our complex k. So it is a collection of all vector spaces on complex k. And also we have linear maps, and also we have linear maps, which is because of boundary operator, linear map. And here I'm denoting, instead of del I'm denoting it with d. So dk mapping ck to ck minus 1, or instead of writing it as small k, you can also write a dn map cn to cn minus 1. That's just a difference of notation. So if you're denoting complex with k, and if you're confusing this k with this k, then you can use n to denote the dimension. So dn map from cn to cn minus 1. So in our chain complex we start from the biggest vector space. So if a vector, if complex is something like this, v0 v1 v2, then v0 v1, then v0 v2, then v0 v1, and v0 v1 v2, right? Over that we have the possible vector spaces are c2, which goes to c1 if we apply boundary operator d2, and if I apply boundary operator d1 on c1, I get 0, and for c0 we explicitly map it to 0. because no boundary is possible for zero simplexes. So d0 maps to 0. Here we have vector. Here we have bases are only one base, v0 v1 v2. Here we have bases v0 v1, v0 v2, and v0 v1. Here we have bases v0, v0 v1, v0 2, and v2 v1, v1 v2, right? v1 v2. Then here we have vector basis v0 v1 and v2. So these are the bases. So C1 is a vector space who have basis v0 v1 v2 v2, and in this vector space I can have many vectors. I just have to so in general, what kind of vector in C1 I have? In general, what kind of vector do I have in C1? So I have basis v0 v1 v0 v2 and v1 v2. So in general I can say that one vector that belongs to here is n1 times v0 v1, so base 1, plus n2 times v0 v2, plus n3 times v1 v2. So these are some general coefficients where these coefficients are, I haven't fixed any one single value. So general coefficients. So some coefficients are applied. They can be negative or positive. So this is a one chain or one vector that belongs to C1 vector space. Similarly, I can apply a coefficient to this space or these bases, and in each vector space I get some. I can generate many vectors depending upon on varying these coefficient values, right? So this is my chain complex where I line up all the vector spaces in decreasing order. So if your complex have even more high dimension, if you have some 3 simplex, then you can start with C3, then go to C2, then go to C1, then go to C0, then finally to 0. Here see, we don't have any 3 dimension simplex, so we haven't included C3. Basically here C3 has no basis, C3 is 0. So this way this is your chain complex. You have your so in your chain complex you have all those vector spaces, all vector spaces Cn, and you have all boundary operator Dn. So combining all them, you get the chain complex.